Welcome back. The first speaker for today is Tina O'Keefe, and who will be telling us about degrees of h-polynomials and edge ideals.
Okay, so I want to thank the organizers for giving me an opportunity to speak. It's nice to be out of the US for a little bit. So let's start. So yes, I'm going to talk about degrees of h-polynomials of edge ideals. These are my collaborators. So Jen, who we just saw there, and then Selvi Kara at Bryn Mawr University, Joseph Skelton, who just started a lecture job at William & Mary, and Gabriel Sosa Castillo, who's at Colgate. So, okay, so I'm just going to jump right in and do a bunch of definitions. So we have a graded ring I, and when we have n variables, the whole talk, n variables. And so the Hilbert function of the graded ring R mod I is going to be, it inputs an integer, it outputs the k vector dimension space, or k vector, the dimension of the k vector space of the ith degree, right? And you can, you can count these by counting. You get a basis by counting standard monomials of the ideal, or of R mod I. Okay, so then the Hilbert series is just the generating function of the Hilbert function. And so here we see, oh, I'll try to use this thing. So here we see here's the generating function, and then what you can do is you can write it in this reduced form, where you get a polynomial in a numerator, and down here you have 1 minus t to the d, where d is the Kroll dimension of the quotient ring. And so that numerator is what we're going to call the h-polynomial. And so I'm going to call the degree of R mod I the degree of this h-polynomial. It's a very overloaded word, degree. It means very different things in very different contexts, right? So in this context, for this talk, the degree is the degree of the h-polynomial. Okay. So I'm going to also briefly define regularity, because we're going to look at regularity and degree together. So this is my minimal free resolution. I'm like having trouble deciding where to stand. So this is a minimal free resolution. It's this exact chain complex. You have these free modules with these ranks of beta ij. These are the Betti numbers of R mod I. And then there's lots of ways to define Betti numbers, and regularity, I like this. This is, so the regularity is the maximal shift in the twist of the degree twist of the free modules in the ith homological degree. Okay, the difference. Okay. Whew. So then the Hilbert series, right? So now we have a different expression for so we're going to look at 3 different expressions for writing the Hilbert series. So now we can write it like this, right? So it's this -1 to the I, and then you fix that I is your homological degree, and then you add up all the Betti numbers in that shift, and then you take it t to the I plus j, right? So notice down here that this denominator, the power is n. That's the number of variables. So this is not reduced in this form. Okay. Here we go. Okay, so, right, so a natural question here is like, okay, so we have this expression where we can read all sorts of invariants from the minimal free resolution, regularity, et cetera, projected dimension. And then we also have this. And so this reduced expression with the h-polynomial and the degree. And so can we find a relationship between these 2 things, right? So I'm just choosing regularity because that's what's done in the literature and what we looked at. So, okay, so some answers, right? So we know that if R mod I is Cohen-Macaulay, then the regularity is equal to the degree. The converse is not true. Herzog gave a strongly stable monomial ideal in 4 variables, and Hebe and Matsuda in 2018 give like a family of these Cameron-Walker graphs that I'm going to define later, and the edge ideals of those. They are all have regularity equal to degree, but are not Cohen-Macaulay. In that same paper, and Hebe will tell you he loves this type of result, right? Given any 2 integers R and S, can we find an ideal where the regularity is R and the degree is S? And so they do actually build a monomial ideal in lots of variables to satisfy this. And then, and Hebe, Matsuda, and Van Tuyl do the same thing for edge ideals. They construct an edge ideal to satisfy these, to see what's possible here, or that any R and S are possible. And then in that same paper, they show that the regularity plus the degree is less than or equal to the number of variables for an edge ideal. Okay, so this is where our story begins because we saw Adam give a talk in Boston and we thought, you know, this was interesting to look at. So that's the first question we're going to look at today is sort of for which graphs does the regularity plus the degree equal the number of variables, which, and for edge ideal is the number of vertices in the graph. Okay, so let's define edge ideals. So, so G is always going to be a finite simple graph, right? And on n vertices, the edge ideal is generated by the edges. If xi, xj is an edge, then xi times xj is a generator. We call a set in the graph and the vertices of the graph independent if like there's no edges between any two of them. Okay, and then so the maximum size of an independent set is the independence number that we're going to denote alpha G. You'll see that a lot. And then so the independence complex, right, is just basically the simplicial complex that I get from taking these independent sets as my faces. And so we like this because now the edge ideal is a Stanley-Reasoner ideal, and lots is known about Hilbert series and Hilbert functions of Stanley-Reasoner ideals. So, okay. So here's just a little example, right? This is C6, right? The cycle on 6 vertices. That's its independence complex. X2 and X5, that's an independent set because there's no edge between them. It's actually a maximal independent set because, you know, those two are adjacent to every other vertex. And so those two correspond to that edge in the simplicial complex, the independence complex. Those three, that's another maximal independent set corresponding to the triangle, etc. Okay. Here we go. Okay, so then what we get is we get that for Stanley-Reasoner ideals, we have yet another expression for the Hilbert series where you get to, so these GIs are the size. So usually this is given in terms of face numbers and there's a -1 shift where that's dimension, but my brain can't handle that. So I'm calling GI, I don't like those -1 shifts. So GI is going to be the size of the independent set instead of the dimension of the face, right? Which is usually how this is expressed. And so, and we define G0 to be 1. And so you get this other expression where you sum from 0 to the size of the independence number because that's the dimension of the simplicial complex, right? So, okay. So for example, in this case right here, I mean, I can just point. So in this case right here, we have the C6, we have our independence complex. And so expanding out this, right? So we have the one here from that G0. Oh, that went away. Why did that go away? Weird. Okay, so then 6, right? This 6 comes from the 6 vertices in the independence complex, the 9 edges, that's you see there, and then your two-dimensional faces. Okay, and then so if you find a common denominator, which my calculus students can't do, you get this expression here, and then so this is the h polynomial right here, h1 plus 3t minus 2t cubed. Okay. So now we have these 3 expressions for the Hilbert series, right? So the h polynomials in the middle, we have this one in terms of the Betty numbers, and then we have one in terms of these shifted face numbers. And so, but from this last expression, we see that the degree is less than or equal to the independence number of the graph. And so that's our question 2 that we're gonna give a partial answer for which graphs does the degree achieve the upper bound. Okay. Okay. So we actually can just fully answer the question 1. So here it is again, for which graphs does the regularity plus the degree equal to n? And to do that, I'm going to define these Cameron-Walker graphs. So a Cameron-Walker graph is of one of the following forms. So it's either a star graph, like a claw, like we saw in Rodica's talk, right? Or it's a star triangle, which is basically a star, but instead of edges coming out of a central vertex, you just have a bunch of triangles coming out of the central vertex. Or it's this connected, right? So in the middle, you have some connected bipartite graph. And then off of one of the bipartitions, every of those vertices have to have at least one leaf. And then down here, and the other bipartition, they can have triangles hanging off of them. They might not. Okay. So why do we care about that? Okay. So Katzmann gave this lower bound, and Ha and Van Tuyl give this upper bound for the regularity. So nu of G is the induced matching number, mu of G is the matching number, so I didn't define B as a matching number. It's a collection of, or a matching in a graph is a collection of edges that no two share a vertex, right? And the matching number is the size of the biggest one. An induced matching number is a similar thing, but now all of your edges have to be at least 2 edges apart. So that if you take the induced graph on the induced matching, you just get those edges and no other edges in between. And so these Cameron-Walker graphs, this was actually a graph theory paper, they proved that a graph has induced matching number equal to the matching number if and only if it's of one of those forms. Okay, so this is, so that gives us the regularity if we can calculate the matching number, which is usually easier to count than the induced matching number. So, okay, so that's our first theorem, is that if G is a connected graph, then we achieve this upper bound for the sum of the regularity and the degree, if and only if it's a Cameron-Walker graph with no triangles. So it's either a claw or it's a bipartite graph where you have a bunch of leaves off of the one bipartition. Okay, so this actually, the proof of this is like standing on the shoulders of giants, right? So basically, Hebe, Kimura, Matsuda, and Van Tuyl tell us how to calculate one of these. I think the degree for the edge ideals of a Cameron-Walker graph, and then Hebe, Kimura, Matsuda, and Tsuchiya give us a way to calculate the regularity for the. And so we just did a little case analysis and it just kind of fell out. So, okay, so that's our definitive answer to question 1. So we move on to question 2. Okay, so we only have partial answers for question 2 because it ended up being a harder question. So the idea, so which graphs, right? We know that we have this independence number as the upper bound. So which graphs achieve that upper bound for the degree? So recall these GIs are these shifted face numbers, right? It's the size of the independent sets, and we're defining it. And so now I'm going to define this G to be this alternating sum of the GIs. Okay, so so we were able to show, right, that we can characterize when we achieve the upper bound in terms of this alternating sum, and it's exactly when that alternating sum is not 1. So now the question is like, okay, so which graphs have that alternating sum not 1? Okay, so and then, but as a corollary to the proof of this, which is like technical and like sums of binomial coefficients and canceling and things like that. But from that proof, we get that if G, we can still calculate what the degree of the H polynomial is if G is equal to 1. And it's the independence number minus 1 minus this like technically defined constant that I'm not going to go through here. Okay. Okay. So, right, anytime you're like, I'm going to prove something about edge ideals, what do? You look at paths and cycles first because they're like the easiest structure to look at. And so we showed that if G is either a cycle or it's a path, so a path is just a line graph on n vertices, right? And so as long as n is congruent to 0 or 2, not 1 mod 3, then we get that G is not equal to 1. Okay, so in this case, so we get to say that the independence or the degree of the cycle is the floor of n over 2, which is, these are the independence numbers for the cycle. Oh, sorry, back. And then for the paths, in the case where G is not equal to 1, we get the full independence number. And the case where n is equal or congruent to 1 mod 3, we get the independence number minus 1. Okay, so then what do you look at after that? Usually you go to trees, but we were more ambitious, so we went to bipartite graphs in general. And so, oh, I'm going to be done early. Okay, so G is a bipartite graph on this vertex set union V, right? So if every vertex in V is whiskered, so that just means that everything has a leaf, okay? So then you get that the degree is the independence number right away. Right, so that's like those Cameron-Walker graphs without any of the triangles. Or if you have unwhiskered vertices in V, then the degree is the independence number if and only if this other constant, which I'm going to show you how to define it in just a minute, is non-zero. So again, this is just it's like we translated what did it mean for that G, that alternating sum of the shifted face numbers, to not be 1, into this other sort of more combinatorially defined invariant and it not being 0. So, and then, but as a corollary of that, we get that if G is a complete bipartite graph, that the degree is the independence number. Okay. So, what the heck is Q? So here's my example, right? And we're going to sort of organize the vertices and give them names in a certain way. Yes.
What is this Q of the defined?
I'm about to define it. No, I wasn't. It's pretty technically defined, and so I was. So it is this Q, and now I'm defining Q. Okay. So the first thing, I have my bipartite graph. So the first thing I'm going to do is I'm going to denote by VW all of the vertices in the V bipartition that have a leaf, that have a whisker, and then VW bar is the complement. Okay. So then once I do that, then for each of those things in VW, I'm going to choose a leaf. Now this choice is not unique, right? Like for V3, I could have chosen U2 or U6. It doesn't matter in the proof because you're just using these sets for counting. Okay, so so once I do that, and then the rest of U is the complement, and so again, it's a little technical, right? So we're going to define X. X is going to be subsets in the non-leaves that the non sort of marked leaves, right? The non-marked leaves, such that like these are non-empty subsets, and the neighborhood of that subset, so all of the things that those vertices are adjacent to are exactly the non-whiskered vertices. Okay, so one more time, because that's kind of technical, right? So I'm going to look at all the subsets of these guys, non-empty subsets, whose neighbors, right? If you take the neighborhood of the whole set, all of the things it's adjacent to, it's exactly the non-whiskered vertices in V. Okay, so then Q, Q is I'm going to look at those of even cardinality, and I'm going to subtract from that those of odd cardinality. Okay, and so that's Q. Okay, so in this example, what's X? It's the empty set, right? Because it's like, oh, you think it might be U3, but the neighborhood of U3 is actually, it includes V3, something that's whiskered. So it's the empty set. So in this case, Q is 0. So the degree is not equal to the independence number, which in this case is 7. That's what these are showing you, these purple vertices. That's the maximal size independent set. And Macaulay 2 tells me that this is the reduced Hilbert series, right? Which shows me that that is the maximal size independent set. It's 7 because that's the degree down here. And then, but the degree of Armada I, the H polynomial, is 5. So we don't achieve that. Okay. And then with 2 minutes left, I'll finish there. Yeah. Okay.